Hello and welcome to this lecture. In this lecture, we're going to study about the adjoint of a linear transformation. The previous module, we just saw quickly how the inner product can be used to probe a linear transformation, understand it better, and there was this Riesz representation which gave you a very nice, interesting view of how to represent a linear functional like that. And now we're going to push it a little bit and define something called the adjoint. Okay, the adjoint actually depends very much on this Riesz representation and see how it works. Okay, so let me describe the picture first and then I'll come back to this. Okay, so you have a linear transformation T from Fn to Fm. Okay, Fn to Fm is a linear transformation. The adjoint is actually a mapping. Okay, right now it's a mapping. We'll denote it T star. It's a mapping that's going to take something in Fm to Fn. Okay, it's a sort of like a reverse mapping. Okay, T goes from Fn to Fm. Adjoint is going to go the other way. Fm to Fn. Okay, it's only a mapping at this point. How is this mapping defined? It uses the Riesz representation. So what you do is, if you have a V in Fm, and I want to find T star of V. Okay, how do I find T star of V? I first look at T of U comma V. Okay, and use the Riesz representation to find a WV. Okay, I know this inner product T of UV has to be equal to inner product U comma WV, right? So there has to be a WV here. And this is unique and it's guaranteed by the Riesz representation. We didn't really prove the uniqueness. It's not too difficult to show. It's a bit of a theoretical exercise. I'll leave it as an exercise, but it's unique. So what does T star do? It maps V to WV. Okay, I know that this Riesz representation is guaranteed. T of U comma V is V comma WV, and for every U this is true, and for a particular V I get a WV. Now all that this T star does is it takes V and sends it to WV. Okay, that's what it does. T star is a mapping from Fm to Fn and it sends V to WV. That's all. Okay, the Riesz representation is used in a very smart way to define the adjoint. Okay, so the most important and defining relationship of the adjoint is this guy, and you'll see we'll use this over and over and over again in many proofs. Maybe I'll go through them a bit quickly, but you'll see this is a very important defining relationship. Notice what happens here. The inner product between T of U and V, which is actually in Fm, is equal to the inner product between U and T star of V. This is an inner product in Fn. Okay, this is how the T and T star interaction is defined. So if you anytime you have T of U comma V in inner product, you can send this T to the other side, but it will become T star. Okay, so it will become U comma T star of V. You see that? So that's the defining relationship. A lot of people just understand this and work with this, but you should see how the representation theorem gives you the existence of this T star of V. Okay, so what type of a map is this T star? It seems like a interesting enough definition. It seems a little complicated right now, but we'll simplify it with matrices and coordinates soon enough. But before that, we should first see what type of a mapping is T star. As you can guess, adjoint is actually a linear transformation. Okay. So we have T from Fn to Fm, T star from Fm to Fn, satisfying this relationship. From this relationship, you can establish linearity. T star is a linear transformation, right? So T of U comma V is U comma T star of V. We can establish that T star is in fact a linear transformation from Fm to Fn. Let's look at a very quick proof. I'm going to go through this very fast. Let's start with U comma T star of AV1 plus BV2, right? Let's see how this simplifies. I can take this T to this side, right? So that's what this relationship tells me. It becomes T of U comma AV1 plus BV2. And now I use whatever linearity I have for whatever conjugate linearity or linearity I have for the second part. So this becomes A bar T of U V1 plus B bar T of U V2. Now again I have these two guys. I'll use my same T star relationship. This T star will go to this side, U comma T star of V1, U comma T star of V2. And then again I use the conjugate relationships and A to this side, and then the additivity in the second argument. I get back to this side. Okay, so if you start with T star of AV1 plus BV2 for every U, you end up with A T star of V1 plus B T star of V2. So this T star of AV1 plus BV2 has to be equal to A T star of V1 plus B T star of V2, and the proof is complete. Okay, so this part needs a little bit of a technical argument. We'll skip that. So these two are also equal. Okay, so now that T star, which is our adjoint, is also a linear transformation, sort of a reverse direction, right? From Fn to Fm, you went with T. With T star, you're going from Fm to back to Fn. Okay, what is the matrix of T star? Is it connected to the matrix of T? So that's the sort of question we're going to ask. Now don't confuse T star with T inverse. Okay, so a lot of people have that confusion. So these two need not be related at all, right? First of all, this Fn to Fm, if M is different from N, it's not even invertible. Right? There's no question of invert. But this T star has a very nice property that it gives you the reverse direction transformation, and it is connected to T in some way. Okay, so it's a different connection. Okay, so we'll see what the matrix is and how it works right now. Okay, so matrix of that adjoint you can easily find. Okay, so here is how you find it. Let me start once again with T from Fn to Fm. This is my transformation in the forward direction. I will do only orthonormal basis. I already know I'll have orthonormal basis for these guys. So I'll pick E1 to EM, F1 to FM. You can think canonical if you want to. And matrix of T with respect to the orthonormal basis we've seen before is very, very easy, right? So T of E1, F1 and the first entry like that. T of EI, Fj. That's the ijth entry, right? So it's easy to, yeah, so you can see ith column is T of EI and the jth row is T of EI, Fj. Right, so that's what it is. So it's easy once you have orthonormal basis to figure out what the matrix of the linear transformation is. Okay, so now how do I go towards T star? I know T star is from Fm to Fn. I'll retain the same basis, but F will become the input basis and E will become the output basis, right? So that's the only thing that will change. And I have this relationship between T and T star. I know that. And M of T star also in this basis is easy to write down, right? So you notice the difference here. I'll have T star of F1 in the first column. Likewise, T star of F2 in the second column. The last column will be T star of Fm. And the inner product now has to be with E1 to En. E1 to En. So notice that this guy is an M cross N matrix. And this one is an N cross M matrix. Okay, so notice I've written it all in the same, graphically in the same way, but they have different type of entries. Okay, so I hope you see that. This is just how to find matrix of a linear transformation with respect to orthonormal basis for input and output. Okay, so how do you relate these entries to these entries? That's the question here, right? So that question we're going to resolve now by using this relationship. The first thing is, let's look at the ith column and jth row, right? What is the ith column, jth row in this matrix? T star of Fi, Ej, right? So this entry. Now I'm going to use this one, but this seems to have a little bit of a reverse, right? It's not U, T star of V, it is T star of V, U. But that's not a bother because I can conjugate both sides, right? If I conjugate both sides, you see that this relationship is the same as V, T of U, okay? It's the reverse, right? So V, T of U is the same as T star of U, V, U. Hopefully you see that because conjugation gives you the reverse, right? So when you reverse the ordering of the inner product, you get the conjugate of the inner product, right? So if I conjugate both sides, I get that the reverse is also true. So even in V, T of U, you can take T to this side and you'll get T star of V, U, okay? So here I have T star of Fi, Ej. Now I'll use this part and send this T star to this direction. I get this becomes the same as Fi, T of Ej. See, I need to go to T of Ej, Fi types thing, right? So I have Fi, T of Ej. How do I go to the other direction? I have to conjugate, right? So if I want to flip this, I have to conjugate. So I get inner product T of Ej, Fi conjugate. So what is this entry here? This entry is the j, ith entry, jth row, ith column, right? That entry of M of T star is actually the conjugate of the I, jth entry, the ith row and jth column of M of T. So entry wise, these entries are related. The entry of M of T star, the j, ith entry is related to the I, jth entry. So you flip the row and the column. So you're looking at the ith row, jth row, ith column. You have to go to ith row, jth column. So row and column have to be interchanged. Okay, when you want to go from M of T to M of T star, also conjugation has to be done. So you interchange row and column, you conjugate. So interchanging of row and column is called transpose of a matrix. Conjugation is of course conjugation. So from there you get that this matrix is nothing but the conjugate transpose of this matrix. So you see the first row has come down to the first column and the last row has gone to the last column, and then the M cross N becomes N cross M, and then you get conjugation. So that is nothing but M of T Hermitian. So conjugate transpose is what's called Hermitian in our terminology, M of T H, and M of T star is a conjugate transpose of M of T. So this gives us a solid handle. So you have an M cross N matrix taking you from Fn to Fm What does the adjoint do? It's simply the conjugate transpose of this. It takes you from Fm to Fn, but it's just the conjugate transpose of this matrix. Now, the orthonormal basis is very, very, very important. If you don't have an orthonormal basis for your definition of T, you can't use this. So that's something very important. A lot of people make this mistake. If you have a linear transformation with any other basis which is not orthonormal, then this kind of an operation is not true. You can't do conjugate transpose. Okay, only when the orthonormal thing is there. So notice the fact that each entry was an inner product here was very crucial, and that comes only for orthonormal basis. Okay, so I hope you see that. Okay, so now we know how to do adjoint, how to do matrix for adjoint. Okay, so now it turns out, and with matrices you can do a lot of algebra, right? You can add matrices, you can multiply matrices, you can add and multiply, you can do a lot of interesting things like that. You can also do with adjoint. Adjoint is nothing but another operator, so you can do all those things, and all those operations are related to the original ones also. So here is the sum property. All these things can be proved. I'm not going to emphasize too much on the proof. It's just an obvious sort of intuitive result, so we'll go with that. If you have two linear transformations, st from Fn to Fm, s plus t whole adjoint is the same as s adjoint plus t adjoint. Okay, so the proof uses the defining property over and over again, and I'm not going to emphasize this too much. S plus t is s of t plus t of u, and then s of u comma v, t of u, and then s star goes to the other side. You combine it, you get that. So you see that for s plus t, it has to be s star plus t star, like this. So it's just the same defining property manipulated and used over and over again. So in terms of matrices, what this means is a plus b Hermitian is a Hermitian plus b Hermitian. It's a very obvious property that you can prove very easily. Scaling is a little bit slightly different, because if you do lambda t and then you do adjoint, you will get lambda bar times t adjoint. Okay, because in a lambda a Hermitian, you're conjugating each thing, so the conjugate of lambda bar will multiply a Hermitian. The proof is also here. I'm not going to go through it. You can see it. Product is a little bit interesting. If you do S product, because product of matrices, by the way, in linear transformation, it's composition. If you compose S and T and then you do adjoint, S circ T adjoint is the same as T adjoint circ S adjoint. Okay, so the ordering reverses. Okay, so this is something to keep in mind. Notice if you have to do this composition S composed with T, the output of T should match with the input to S. So that is something to keep in mind. Output of T matches with the input to S. Okay, so S circ T whole adjoint is T adjoint circ S adjoint. The ordering reverses. So what it means in matrices is AB whole Hermitian. If you product and then do Hermitian, it's the same as B Hermitian times A Hermitian. So this one reverse alone you have to remember. Okay, so this is something important to keep in mind. Okay, the proof is here. You can go through the proof. It's sort of again uses the same relationship over and over again. So these properties tell you how to deal with just algebra of adjoint and all of those things. Here are a couple of more properties which are important. What happens if you repeatedly take adjoint? You take adjoint and then take the adjoint of the adjoint, you'll go back to the original T. This is very easy to see that if you do two Hermitians in a row, you go back to the original matrix. You're doing a row column transpose and conjugating. Both of these sort of, when you repeat it, they go back to the original one. So you do the reverse transform and then you do that, it works out. So in terms of matrices, it's easy to understand. The proof in terms of the operator, the property is also quite easy to write down. Okay, I'm not going through it. You read it if you have some interest in time, but the property is very, very important. Okay, if you take the identity operator has itself as the adjoint. So it is one of those self-adjoint operators. These operators are called self-adjoint. The adjoint is equal to itself. Okay, so these are very, very, very special operators. We'll see this soon enough. But identity operator you can easily show as self-adjoint. Okay. So here are a bunch of examples. I'm not going to do this. I mean, this is just for practice for you. But make sure you practice these things and get comfortable with the idea of using adjoint and other matrix operations interchangeably. You should be able to easily do these kind of evaluations and be very, very comfortable with it. Okay, so this comes to the end of adjoint. Adjoint is a very vital linear transformation which sheds a lot of light on the original one. Okay, by studying the adjoint and relating it to the original, you can learn a lot of things about the original operator and how that linear transformation is working. Okay, thank you very much.